So, hello from Ankara. Welcome to our webinar. Our topic is patient result-based quality control. I would like to thank all the participants for joining us this evening. My name is Merve Sibel Gungoren, and I'm the chair of Working Group Promotion and Publications. I would like to present today's speaker. Let me introduce him briefly. Professor Abdurrahman Coşkun is a professor of clinical biochemistry at the University of Acıbadem Mehmet Ali Aydınlar University, Istanbul, Turkey. His main research area is biomedical metrology, and he is mainly focused on statistical process control, biological variation, uncertainty, Six Sigma, and standardization of proteomics data. He's an expert member of EFLM Biological Variation Working Group and EFLM Biological Variation Database Task Group. He's also interested in transplantation proteomics and has developed and patented a solid organ preservation solution. Welcome, Dr. Coşkun. First of all, I would like to clear a pronunciation mistake. His surname is Coşkun. It's not something else. So, welcome, and please proceed. Thank you.
Okay. Thank you, Merve. Welcome, everybody. Good evening. My presentation is monitoring of internal quality control system using patients' data. And presentation outline: internal quality control, frequency of internal quality control and patient safety, monitoring of internal quality control, periodic monitoring of internal quality control using QC samples, and continuous monitoring of internal quality control using patients' data, and finally, conclusion. So quality control, it can be defined as the control of the testing process to ensure that the measurement results meet the expected quality requirements. Here, the critical point is that we want to be sure that the reported patient results meet the expected quality requirements. And QC processes vary depending on the method. It may be quantitative, semi-quantitative, or qualitative. And within these methods, for semi-quantitative or qualitative methods, we use non-parametric models because the data of these type of methods do not show a normal distribution. And therefore, we use non-parametric models. But today we are going to focus on quantitative methods. According to ISO 15189, the laboratory shall design quality control procedures that verify the attainment of the intended quality of results. So, internal quality laboratory medicine, and this system helps us to detect, reduce, and also correct errors in analytical process prior to report patient's results. So now, internal quality control, the first point is the frequency of analysis of QC samples. It may be daily, weekly, monthly, or once per shift, twice a day, 3 times a day. And now many labs prefer once a day. The second important point is the number of controls. For clinical biochemistry tests, we can use 2 levels, but for hematology parameters, we prefer 3 levels. Absolutely, we need some rules to evaluate the QC results for acceptance or rejections. For this reason, we can use also Westcott multi-rules or other simple user-friendly rules also is possible. Now we are going to focus on the frequency of analysis of QC samples. So, how often is right? According to ISO 15189, quality control materials shall be periodically examined with a frequency that is based on the suitability of the procedure and the risk of harm to the patient from an erroneous result. Here the critical point is that we should examine quality control materials periodically, and the frequency of analysis depends on the suitability of the procedures and the risk of harm to the patient results. So, the frequency of internal quality control unfortunately are not standardized, and it is usually based on regulatory requirement. Clear regulation mandates the minimum frequency of internal quality control evaluation in terms of time. Here you can see also the program. It may be periodic or continuous. In periodic one, we use QC samples. We can analyze these samples in terms of time or in terms of the number of analyzed samples. And in the literature valuable papers, for example, one of them published by Parvin, it's about the impact of the frequency of quality control testing on the quality of reported patient results. Here there is a link between the impact of the frequency of quality control testing and the quality of reported patient results. The idea is excellent. It is really very good, very important. But in this paper you can see there are various complex equations. Personally, I am a pragmatic one. We need simple, usable, user-friendly equations which can be used by laboratory staff in daily practice. Later, Westcott published a paper about statistical quality control, risk-based statistical quality control, and in his paper they proposed a nomogram. You can see here the nomograms. Run size and sigma metric. The run size depends on the performance of your methods. You can use also this nomogram to make your decision, but once again, we should be careful about the sigma metric calculations. It is clear that sigma metric obtained from Westcott equation is totally nonsense. This point is very important. So once again, this figure, we should focus on continuous monitoring. Now we use periodic monitoring. We use QC samples, and we analyze these QC samples in terms of time or in terms of the number of analyzed samples. But now it is time to focus on continuous monitoring. For continuous monitoring, it is not easy to use commercial quality control samples. It is not also cost effective. If we want to monitor our system continuously, we need patients' data. So we have to develop new algorithms. We have to focus on this topic. How can we apply patients' data to monitor our system? The critical point here is that we use patients' data as the own control of patient results. This is a hypothetical example. How can we apply patient data to monitor our results? This is a hypothetical example for glucose. We have QC program. Oh, I am sorry. I think there is a problem in the connections. Okay, or a regular QC interval. This is patient's data. How can we apply this data to monitor our system? It is a theoretical approach. In the first analysis, there is no problem. In the second analysis, there is also no problem. In the third one, we can see there is a problem here. Now, if we use patient's data to monitor our system, we can see that in this region, there is no problem about quality control, and patient's data are located within this limits. But in the next region, there is an elevation. So if we use patient data to monitor our system, we can detect errors at this point. But in current practice, we can detect errors too late at this point. The problem is that within this time, the result of many patients, of all these patients you can see here, now, they have been reported to the physicians. So it will not be easy to reanalyze all this data again. If we use patient data to monitor our system, we can detect errors in time. So this is the reason why we need continuous monitoring to evaluate our system. Another example, a hypothetical example here, or quality control intervals. There is no problem in the first and second evaluations. But in the third one, we have a problem here. When we analyze patient data, we can see fluctuations. Now, if we use patient's data, we can detect errors in this region. But if we use commercial system, quality control system, we can detect errors, but it may be too late. And once again, within this period, many patient results will be reported to physicians. So it is clear that we need a continuous monitoring system. This is very important for patient safety also. Now this is real data, data of sodium. At first glance we can say that there is no problem. But when we analyze these data in detail, we can say that there is a shift between these two regions, a clear shift. So if we use patient data, we can detect these errors in time before reporting patient results to the physicians. Okay. In the literature, you can find many valuable papers, laboratory quality control using patient data to assess analytical performance, changing the paradigm of laboratory quality control through implementation of real-time test results monitoring, patient result median monitoring for clinical laboratory quality control, patient data algorithms. I mean, in the laboratory, we can find many algorithms. But it is time to focus on this topic, and we need something in hand. We need really some usable, practical application which can be implemented in our quality systems. So, if you want to apply patient's data to monitor your system, you have to explain, you have to give the answer of these questions. We have some key questions. So how can we calculate the target of patient's data? How can we calculate truncation limits? With truncation limits here, it means that we should not include all patients' data because we are interested in patients' data. Absolutely, we'll have many extremely high, extremely low level data. So it is not necessary to include all these data in our system. So we need a truncation limits. So how can we calculate truncation limits? Then how many patients' data is required to detect errors? This is also very important. Can patients' data be used to detect random and systematic errors? Now we are going to explain all these key questions one by one. First of all, I want to give a statistical algorithms, very useful, and it is very easy to implement. You can make all these calculations easily. In the first step, we should determine the target value of patient's data. Then we should determine the truncation limits, and then we should calculate the mean, standard deviation, and confidence interval of patient's data located within truncation limits. In the evaluation phase, we'll compare the confidence interval of patient's data and the target value. I will explain later. But this point is very important. There is no perfect model which can be applied to all parameters in laboratory medicines. In any case, even for the best model, we need alternatives. How can we apply this algorithm? In the first step, we should calculate target value, as you see here. And we should also calculate the upper truncation limits and lower truncation limits, as you see here. It means that we'll include patient's data located within this region to monitor our system. We'll exclude other data. So next, we should calculate the confidence interval of target value. Now, we have our system. Lower truncation limits, upper truncation limits, target value, and the confidence interval of target value. Now we can also monitor our system. This is the mean of patient results, PM, the mean of patient results. And we should calculate the confidence interval of patient results here. (95) probability, okay, percent probability, confidence interval you can see here. So, if the confidence interval of patient's data overlaps with the confidence interval of target, as you see here, it means that there is no significant difference between patient results and the target value. So our system is stable, there is no problem. Because the confidence interval of patient's data overlap with the confidence interval of targets. This is the upper limit of confidence interval of target. This is the lower limit of confidence interval of patient's results. Now, there is no problem. But in another group, in this group you can see here, patient's data mean. This mean is calculated from patient's data. And also the confidence interval of this group, these patients, confidence interval, you can see here. And now we can say that there is no overlap because the lower limit of patient's data, the lower limit of confidence interval of patient's data is higher than the upper limit of confidence interval of target. There is no overlap here. So there is a problem here. There is a shift in this region. So we can accept these data as a signal when we monitor our system. Now, I hope everything is clear. Now the problem is that how can we calculate the target value of patient's data? In the literature you can find many different algorithms. Mean of all data, mean of data within truncation limits, average of normals, moving average, exponentially weight moving average. Medians of all data. I am sorry, I think there is a problem about my webcam. Okay. Exponentially weight moving average, medians of all data, moving median, and others. So you can use one of them, but we should not include the data of all patients to calculate the target value. Now, this is real data, results of sodiums. As you see here, if we include all data to calculate target value, we'll also include extremely high and low levels. So this may change the target value. That's why we need truncation limits. We need a specific data. So this is a hypothetical example. How can we calculate target value? If you want to calculate target value, we should be careful. This point is important. We should not include all data. So we need a truncation limit. As you see here, these extremely high level data should be excluded. So we should calculate the truncation limits, upper truncation limits, and lower truncation limits here. We can use these data located within this region. But one important point is that we should be careful about the suitability of our instrument within this region, so we can check our system using commercial quality control samples. You can see here. And if there is no problem about quality system here, then we can also calculate our target value using this data located within truncation limits. Now it is very easy for us. Now, how can we calculate truncation limits? You can accept reference interval, and there are many other algorithms in the literature. And now we can use also between subject biological variation data to calculate the truncation limits of analytes. Today, I will try to summarize this important point. How can we apply the data of biological variation to calculate truncation limits of analytes? When we use reference interval for sodium, here, we use all these data to monitor our system. Okay. And now we can see that within truncation limits, when we use this data, we can monitor our system. So in the first part here, there is a shift. In the second part also there is a shift here. I mean, when we use reference interval as the upper and the lower truncation limits, we can use the data located within this interval. And as you see on this figure, we can use this data to monitor our system. Another approach, truncation limits based on between subject biological variation data. We are really very lucky now we have a database for biological variation. And this is a refined database, EFLM Biological Variation Database. In this database, you can find both within and between subject biological variation data of 130 different analytes. I think we should use this data more frequently in our laboratory in daily practice. So how can we calculate the data of between subject biological variations to calculate the upper and the lower truncation limits? As you see here, between subject biological variation is the variability of a measurement between the homeostatic set points between different healthy participants. Now, on this figure, you can see many healthy subjects. The critical point here is that when we apply this data in monitoring of quality control, we have only one data for one patient. It means that, unfortunately, we have not set point. We have only one data. So can we use only one data to estimate the set point of a subject? Is it possible? The answer is yes, it is possible. Using this equation, this is very useful practical equations here. NHSP, numbers of samples required to estimate the homeostatic set points. And this is analytical variations. And within subject biological variations here. And there is also D here. What is D? D is the allowed percentage deviation from the homeostatic set point. It means that we can calculate the variation around homeostatic set point using this equation. Now, we have only one data for one patient. If we rearrange this equation, and if we solve this equation for D, as you see here, NHSP for one result, it is 1 because we have only one data for each patient here. Then we'll obtain this very simple equations here you can see. So we are familiar also with the last equation. It is RCV divided by square root of 2. So how can we apply this equation to real data? This is our paper published about biological variations of hematological parameters. So in this paper, in this table, you can see here N. So what is N here? N is the numbers of samples required to estimate homeostatic set points. D is the variation around homeostatic set points. Now, it is very interesting here for erythrocyte indices. Only the data of only one patient, only one data, using only one data, can estimate homeostatic point within 5% deviations. Here we can estimate the presence of homeostatic set point preciously. But on the other hand, for leukocyte parameters, we are not so lucky. We need too much data. So it means that when we use only one data for erythrocyte indices, the variation around homeostatic set point will be narrow, but when we use one data for leukocyte group parameters, it will be too wide. Especially for basophils, you can see here, if you want to obtain homeostatic set points within 5% deviation, you need 63 data. It is extremely high. So this paper was published 40 years ago in 1974. At that time, they used the data of erythrocyte indices to monitor their systems. Now we understand why the data of erythrocyte indices is so in a narrow range. Now, how can we use this data to calculate the truncation limits? The approach is similar to the calculation of reference change value. In reference change value, we calculate the maximum difference between two samples obtained from the same subject. The maximum difference, the total variation of two samples obtained from the same subject. Similarly, in this case, we can also calculate the total variations of two different subjects. In other words, we can also calculate the maximum acceptable limits between the results of two different subjects. But in this case, this subject must be healthy. This is very important point because we calculate biological variation data from healthy subjects. We have also data for ill patients, but now our database is focused on data of healthy subjects. Okay. Now, in this equation, we can see here that these two parameters is about the variation around homeostatic set points, and the next one is the variation of between subjects. When we combine this data, for example, for sodium, using these parameters, we can calculate truncation upper and lower truncation limits for 95 probability, 99, and the lower truncation limit. It is very easy. We can calculate truncation limits, and then we can also apply these limits to monitor our system. A very good example, sodium here. The within and between subjects biological variation of sodiums, you can find this data from EFLM biological variation database. Now we calculate truncation limits using the data of biological variations. Here, upper limits and lower limits, truncation limits. It means that we use only these data to monitor our system. We excluded all data out of truncation limits, higher than upper truncation limits or lower than the lower truncation limits. Now, can we use this data to monitor our system? When we examine this data in detail, we can say absolutely we can use it. This is our target value. And we can see also there is trends in these different regions. And also there is a shift between target and the data of different regions. We can say that sodium level in the second region is higher than the sodium level in the first regions. So all data are real data. As you see here, we can use patients' data to monitor our internal quality control easily. Another example. LDL cholesterol in database, LDL cholesterol within subject biological variation is 7, and between subject biological variation very high, 21%. So we calculated the upper and lower truncation limits. The lower truncation limit is 47, the upper one 208. These are real data, patient's data, our target. And we can see here there is a problem in the first day in LDL results here, you can see. As you see, so far we use only patient's data to monitor our system. It is really possible to monitor our system. In reality, we should do it. So the next question, how many patients' data are adequate to detect errors? This is a critical question. And we can calculate the minimum number of patients' data using the equations of confidence interval. Now, I will explain this situation on a separate slide. This is our target value. And the confidence interval of target value, upper limit, lower limit. Then, this is the mean of patient results. We also calculate the confidence interval of patient results here. Okay. Now we can say that there is an overlap here. The lower limit of confidence interval of patient's data is lower than the higher limits of confidence interval of target. So there is overlap here. And here there is no problem. In the second part, you can see there is a problem. So the question is that how many data is necessary to detect this error? How many samples? We can calculate the number of samples using the equation of confidence interval here. Okay. So this is the number of patients' data. It may be different for different tests. But we should be careful that statistics is not everything. Our experience is also very important. And despite everything, we should not accept the data of a low group. I mean, especially if n is lower than 10. We should not accept. We should include as much as possible, many data, because when we increase n here, the confidence interval will be narrow. Then it will be possible to detect even a small shift. So for this reason, we should be careful, and in any case, it is based on our experience and should be higher, at least 10, and pragmatically even 20. Okay. Now, one important point here is that in all my previous slides, I included the confidence interval of targets. But in reality, we do not need the confidence interval of targets, because when we calculate targets, we should include the data of many patients. So when we increase the number of data, the confidence interval will be narrow. So you can see here, when we include, for example, 15, the data of 15 patients, this is the confidence interval. When we include the data of, for example, 400 patients, the confidence interval will be extremely low. So in my opinion, we can also neglect in this region the confidence interval of targets. Because confidence interval of the mean decreases exponentially with the increased number of patients' data. So in reality, the confidence interval of target is extremely narrow. We can ignore this interval. So we can take only target line here, as you see. Now, it is easy to implement our algorithm. This is the mean of patients' data. And there is no problem here. In the second part, you can see the problem. Now, can patients' data be used to detect random and systematic errors? We are lucky, especially in detection of systematic error, but unfortunately for random error, it is not easy to use patient results to monitor our system. We need complex algorithms. And finally, conclusions. Patients' data can be used to monitor internal quality control. It is a reality that currently there is no perfect algorithm to be used for all measurements analyzed in laboratory medicine. In my opinion, based on my experience, biological variation model can be used effectively to monitor our internal quality control. The number of patient samples here is very important, and we can say that using patients' data to monitor internal quality control increase patient safety. This is very important. And it provides early detection of errors, and in this case, we can solve problems immediately in time. And finally, we can say that using this system will reduce the number of samples to be repeated due to errors. It means that we can decrease the number of problematic results reported to physicians, and we can also decrease the number of samples to be repeated due to these errors. And thank you very much for your patience. Now I am ready for your questions.
Thank you very much, Professor Coşkun, for this presentation. There was a bit problems with the presentation, but I hope everyone enjoyed it.
But it is very interesting. I cannot see myself. There is a problem about camera, but my camera now is on. There is not a problem here, but to be honest, I do not know the reason why I cannot see myself on the screen.
We were seeing you, but right now we cannot see you. If you can try it. Anyway, I would like to request questions from participants. If you have some questions, feel free. So I want to wait for a few minutes for the questions to be written. And I want to ask an introductory question, if you let me. So,
yes, okay.
So what do you think that, what are the challenges of real-life application in patient results-based QC? Is it applicable for all analytes or test groups? What can we do?
Absolutely, it is very easy, but it depends on the ability of your IT department. And it is very easy to develop an algorithm to use patients' data to monitor your system, but finally it depends on the ability of your IT department. Especially for some tests, in my experience, for sodium, calcium, albumin, LDL, and for many tests, we can use the data of patients to monitor our system. But we need a cultural change also, because so far all of us are experienced in commercial-based quality control systems. But in reality, we can also use our patients' data, because our system usually produces many data, and we can use this data to monitor our system. We can also accept each data as the own control of patient results.
So there's a question, and I also have a similar question. So I want to ask, Vladimir Prochenko asks that where is the evidence that we have every day the same kind of patient population? I think.
Yeah, you are right. But, okay,
Yes.
so.
It's also the same question in my mind, because I think that especially in tertiary medical centers, we have too many specialties and subspecialties, and we always receive pathological samples from selected cases. And I think that even within the day, we may receive, let's say, some part of the day when you receive from like an endocrinology outpatient clinic, but you receive most of the samples in the morning, maybe later it's some, let's say, from a family medicine outpatient clinic. So I think the values may vary. So maybe values cannot be homogeneous at all times. So I am aware of the truncation limits, but does this affect our study?
Yeah, this is very important. You can be sure that we do not include all data, and we need some limits. That's why we calculate truncation limits. So using truncation limit is a kind of filter. We exclude all other data. Extremely low, extremely high data are excluded from the system. So in this situation, we use only the data located within truncation limits. Now I want to give I'm sorry. I want to show a slide here. The connection is a bit slow. I want to show you a slide, but now I am waiting because truncation limits. We use only these data located within truncation limits. Higher truncation limits, I mean upper truncation limits, and lower ones. And in any case, we do not include other data. If your patient is healthy ones, or even if they are patients from endocrinology department, nephrology departments, it is not so important, because we use only the data located within truncation limits. That's why I mean, when we calculate truncation limits, we should be careful which data should be included in my monitoring system. So, in my opinion, if we use biological variations model, we can also calculate a reasonable limit. Because in biological variations model, we calculate the maximum acceptable difference between two different subjects. So we can say that all data located within this truncation limits, all data, you can see here, can be used to monitor our systems. For example, for creatinine, if the patient is coming from nephrology department, and we'll use only creatinine levels within truncation limits. We do not use extremely high levels. So I do not mean that this system can be used instead of quality control based system? Absolutely not. We use this system to monitor our internal quality control system. It is a monitoring system. It does not mean that if we implement this system, we should also exclude the QC-based model. Definitely not. This is a monitoring system, and the main reason of implementation of this system is that we want to detect errors in time. Because when we use QC-based system and when we detect errors, it may be too late. And at that time, many patient results may be reported to physicians. So I think reasonable truncation limits will be very useful to monitor our system.
So there are also other questions, so let me ask them quickly.
Yeah, sure.
Rosalino Catania asked that, what about differences coming from ethnic variations? What can we do about this?
I am sorry, please, can you repeat it again?
Rosalino Catania says that, what can we do about differences coming from ethnic variations? Is it also applicable in that state?
Sure. This is really very important point, and unfortunately we have no data about biological variations obtained from different ethnic groups. It is a big problem here, and I hope in the future in our database we'll have also biological variation data for different ethnic groups, but in reality just now we have no data, and we should accept both within and between subject biological variations data as the universal data, not specific to one ethnic groups. But if one day we have data for different ethnic groups, then we can also rearrange our truncation limits. Here, I want to give the basic principles. So, if we use biological variation model, we should accept that there is also some limitations. For example, we have no reliable data about the biological variations of different age groups, different ethnic groups, and so on. So this is a limitation of this model.
Yes. Another question is from Sedef Yenice.
Yeah.
She asked that you said that the statistically minimum number of patients is around 10, but could that be raised up to a maximum number around 100 patient samples? Is there a limit for a given thing, like a specific considered thing about this?
Okay.
So it's about the minimum and maximum number to use for moving average studies.
Sorry, I understand you. Okay. Okay. In my opinion, it is not reasonable to give a fixed number, for example, 100, 200. It depends on the shift. If your shift is high in this figure, as you see in this figure, even 20 or 10, maybe 30, I mean, not so many data. Even a few data may be sufficient to detect errors. That's why we should use confidence intervals. But if shift level is not so high, so in this case we need the data of many patients. So I think the number of patients required to detect of shifts depends on the magnitude of shifts. If your shift is very high, and this should determine a low level. Despite everything, we should not use is higher than. You can see I have a reason. I can say that the confidence interval of these two groups patients overlap. So this shift is not significant.
Okay.
Okay, thank you.
So there is also another question. Milad Farzin asks, can you please tell about the types of methods using patient data like average of normal, exponentially weighted moving average, etc. So what are the main differences between them and what type of method is the more preferred?
So the types of using patient's data. As I'm sorry, okay. As I mentioned previously, in all models, we should in the first step we should calculate target value. A target value is essential. So, in my opinion, target value can be obtained from the mean of data located within truncation limits. But you can also use other models. But when you include many data, for example, your data within 1 year, 5,000 different data, in this case, you will have a perfect target values, because a shift in target value will also affect your system. So I think you can also use other models, but for target value, you should include many data, as much as you could. So we do not include, for example, the data of only a fraction patients, like moving average and so on. We do not exclude some data, for example, reported 1 month ago or 2 months ago. Usually we include all data to calculate in our target value. You can also prefer average of normal, but in my experience, I think we should exclude all data. But to be honest, I didn't make calculation about the difference between different target values. We can do it.
Okay. There's one more question. Is there a time frame within which these data should be collected for setting the target values? It's from Andrea Mersic.
Once again,
is there a time frame? Is there a time frame for collecting the data?
Yes. Yes. Okay. As far as I understand, yeah, there is also some time-free intervals. For example, in this slide, in this figure, we can include the data of these patients to calculate target value, but we should exclude this data. I mean, if our data is out of limit, if there is a significant shift, we should exclude this data from our system. So we cannot include all data sets, as far as I understand, if the question is about this point. So we can accept that this region is free of time. We cannot also include this data because there is a shift in this region.
Okay. I also have another question. What are the benefits of patient result-based quality control? Is it only for real-time use for continuous monitoring, or if you don't have such tools or softwares, is it also some kind of approach for a retrospective use? Maybe we can use for troubleshooting, for spurious results, or I don't know, for a failed internal QC or for a failed external quality control result, can we use this approach also as a troubleshooting tool, like some kind of lot-to-lot variation troubleshooting idea? It's also kind of, there are also some kind of solutions. Maybe is it also possible, if we are not able to use it real time, can we use it retrospectively?
Yes, sure. Now, although the title of presentation is the using of patient data to monitor internal quality control, in reality, we can use patient data to check the variation between lots, even the problems in external quality control systems retrospectively. This is very important. And if you use this system, it will be very easy when you have a problem about external quality control system. It will be very easy for you to point out the problems. What is the problem? Which patient groups affected from this errors, for example, retrospectively. It is not specific to only internal quality control. We can use this system, if we have this system in our system, I mean in our quality control system, we can monitor our internal quality controls, external quality controls, lot-to-lot variations, and even in some cases, if we are experienced in this, in this topic, we can also make cross-checks between the patient's data and the quality of commercial quality control samples. If, for example, the data of my patients, there is no variations, and it seems that there is no serious problem when we compare our data with the previous data. If there is no problems, and if there is a problem about commercial quality controls, in this situation we can ask, there may be a problem about QC samples. So in reality, we should implement this system in our quality control systems, and then really it will be very easy for us to to check the variations of many different parameters. And currently, I think it will help us to detect problems, especially in external quality control systems. Because in external quality control system, when we check our data, we can see the possible shift. I mean, we can also detect the possible shift retrospectively. Then we can also evaluate the amount of this shift, if it is significant or not. So finally, I think it is not specific to internal quality control. We can use also for external quality control and also for other type variations.
Okay. Last question. Last question from Albertos Panagiotis de Castros. How can circadian rhythm or heredity for some diseases such as familial hypercholesterolemia can intervene to this approach, specifically when we have low numbers of samples?
Yeah, this is also an important point, because the variation that we are interested in is random biological variations. And in this random biological variation, we exclude all other variations, seasonal variations, circadian variations, and so on. So this is a limitation of this model. We accept it. But once again, if we calculate a reasonable truncation limits, and if we use only the data located within this truncation limit, then in my opinion it will be easy to follow our system, because this limits, I mean truncation limits, prevent our system, prevent our patients from extreme high and low values, and we do not include all this data. If you calculate upper and lower truncation limits reasonably, then you can also overcome such problems. But despite everything, there are some limitations of biological variation data. For example, I cannot say that we can also apply. I am sorry. We can also apply this model to CRP because the biological variation of this test is extremely high. But for parameters which have reasonable variations, it is useful. For example, we applied this model to LDL. LDL really is a good example, and there is no problems. But finally, I can say that no model is perfect, but the best one, as far as I know, based on my experience, I can say that if we apply between subject biological variations to calculate truncation limits.
Okay, I was just going to ask, just to conclude, just to wrap up this presentation. Our last question is from Dr. Yücel. Is QC with patient samples has advantage to QC materials because of the commutability problems? Before you answer this, I was gonna ask a funny question, but I mean, can we get rid of internal QC routines? Is it possible? What do you say?
Now, in commercial-based quality control systems, we have a big problem, commutability problems. Yes. And we can say that patient's data is the original data, and we can use also this data in evaluation of our QC systems. And we have no commutability problems here. So can you repeat the last part of your questions?
My question is just a funny one. I say, can we get rid of the internal QC routines? When we say monitoring patient results, is it complementary to internal QC, or do we expect that in the future we can get rid of the internal QC and we can only have the patient result-based QC? What do you think?
Yeah. Just now, I can say that we should use this system only as a complementary system. Yes. But in the future, it is possible to use only, how can I say, patient's data combined with in-house quality control materials. Yeah. In-house quality control materials to overcome commutability problems. I am sure it is possible now. It is now we can collect samples, we can prepare in-house QC materials, but just now at the moment we need commercial quality control samples. This is a complementary system. We can also use patient's data to monitor our system, but maybe in the future, even in the near future, we may also use in-house quality control materials and exclude all commercial types.
Dr. Coşkun, I would like to thank you again for this nice presentation, also a very interactive Q&A session. I also want to thank all the attentive participants for their real quality questions. It was very nice to be with all of you. Thank you very much.
Thank you very much for your patience and for your really valuable questions. And we discussed these very important topics. I hope in the future we'll have many papers, we'll have many new studies.